In this video we're going to discuss three of the AVR addressing modes, the simplest ones. So first of all, let's describe that an addressing mode is the mechanism that the microprocessor has by which from the instruction certain fields are interpreted in order to access the operands. So it's something that occurs inside the execution of an instruction, and this functionality is what the microprocessor used to access the operands. Now, before proceeding with the description of the addressing modes, let's describe certain notation that we're going to be using. The address of the operand, we're going to call it the effective address, and we're going to represent it by add sub e. Then the instruction fields, which is what we're going to be looking to interpret, we're going to denote them by inst sub f sub I. Registers, we're going to refer to them as r sub I, and in some cases the field of the instruction is going to encode the name of a register. In that case we're going to refer to that register as r sub f sub I. This is the register specified by the field I found in the instruction. And then the access to memory, we are going to distinguish it with these two notations: pmem for the program memory, and then we provide an address in brackets, or dmem for accessing the data memory, which we know in the AVR architecture we have these two memories. And finally, when there is an operation over a register that takes a new value, we'll denote it like this: r arrow v. Okay, so let's describe the first simplest addressing mode, which is known as register mode, and I think it's the most intuitive one. It is very simple. You get an instruction. Remember that an instruction, most of them, not all of them, have 16 bits, so we're going to assume the instruction goes from 0 to 15 bits. There is one field in this instruction, not necessarily placed where you see it here, but it could be spread all over the 16 bits, and this field over here specifies one particular register from the register file, and in that register is where we find the operand. Another way of looking at this now, in terms of the notation we just described here, the effective address of the operand is specified by the field, let's say f sub 1 on the instruction. This is what we refer to, this field over here. And the operand is actually r sub f sub 1. In other words, the register, the index of which is encoded in this field. An example of this addressing mode, very easy. For example, this instruction R12 R13 has two operands, and both of them are being used or are using the register mode, addressing mode. And again, this is the simplest one. Let's look now at two other addressing modes that are not so straightforward. The first one is what we call the data direct. This is an interesting one because the instruction, which is going to have initially 15 bits, 16 bits, it's going to have a second set of 16 bits. So in other words, the instruction, it's going to be, in this case, 32 bits. Let's call it from 0 to 15, 16 to 31. And the second group of 16 bits, it's going to define a data memory address. In other words, the data direct addressing mode assumes that after the 16 bits encoding the instruction, there are another additional 16 bits with an address, and this address is going to be taken directly to access the data memory. And we're going to find the operand precisely on that location. So if we keep using the notation we used before, the effective address of the operand in this case is actually in the program memory, in the address specified by the address of the instruction. Let's denote it like this: add sub inst plus 1. So this expression, what it's saying is that I need to get the address of the operand that I'm accessing from the memory position following the current instruction. So this is one example in which we take an additional 16 bits from the program memory and we use them to access the data memory. Therefore, the operand, we can say, following this notation, it's going to be located in the data memory in the position specified by that value, which is stored in the program memory in the address of the instruction +1. An example of this addressing mode, very common, it is when we write an instruction like, for example, LDS R12 and then a label. This label over here is using the data direct. Typically, when you write an assembly program, this label is going to be previously defined in the data section, and what you're doing here is loading, in this particular instruction, is loading into register 12 the content in data memory specified by this label. Another way of looking at it, this instruction that you're seeing here is encoded in such a way that the first 16 bits encode the operation code LDS and the register R12, and the additional 16 bits here encode the address which is assigned to this label definition on your program. Now, a couple of interesting things, or one interesting thing about this instruction is that it performs 3 memory operations. The first one is to fetch or obtain these first 16 bits. The second one is to obtain the address that is following the instruction, and the third operation is when it accesses data memory. So as you can imagine, this type of instruction is going to be slower than the rest because it requires not only the fetch, which all instructions have, but an additional access to the program memory to get these 16 bits, and another one to access the operand. The third addressing mode we're going to describe in this video is what we call data indirect. Now, in a data indirect addressing mode, the instruction, typically now with 16 bit, again 0 to 15, it's going to have one field, so from that point of view is similar to this one field encoding one register. So it's pointing to the register file, but the difference with respect to register mode is that in this register what we find is the address that we're going to take to data memory to find the operand. So the reason why this is called data indirect is because even though the instruction has one field encoding something, it is not encoding the destination of the operand, but in fact it is encoding the register in which we will find the address of the operand. So following the notation we used before, the effective address of the operand here, it's going to be the register specified by the field F1 in the instruction. So remember, this notation, what it's telling us is I take the content of this register and the index of the register, it's going to be encoded in certain field in the instruction. And the operand, analogously, it's going to be located in the data memory in the position specified by R F1. In this notation, we always find the operand in these two addressing modes in the memory location specified by the effective address. Now, two interesting special conditions for this instruction. The first one is this instruction performs two memory operations. The first one is the same one we saw here, the fetch operation, because it's present in all the instructions, is the operation by which these 16 bits are loaded from the program memory into the control logic, but the second one is to access the operand. The other very important restriction of this instruction is that memory address in AVR, data memory address are 16 bits. And remember that the register file contains 32 8-bit register. So how do we store 16-bit registers here? And in fact, the restrictions is that we can only use registers X, Y, and Z, which are R31, R30, R29, R28, and R27, R26. In other words, the address that we use for the data indirect addressing mode, it's going to be stored in one of the 3 registers that the microprocessor uses, concatenating 2 registers of 8 bits, and this microprocessor can do it only with these 3 pairs of registers.